Hello again. How's it going, guys? Hope everyone is safe. As I mentioned in my last video, I am going to continue with my deflection. Let me just make sure that you guys can see the board well. So I think it's pretty good, I think. So let's get started. Remember last time we said that we need to prove that the deflection for this beam, it should be, if we use elastic curve method, 5 omega naught L to the 4th over 384 EI, right? So this is your omega naught, that's called intensity or traction or UDL, uniformly distributed load, or EDL, evenly distributed load, and the unit is kip per feet or KLF, kip per linear foot. We just make sure that you guys see all on the board. It looks good to me. Well, give me your opinion. So, well, first step to do is I probably need to bring another board, but due to the spacing, it's kind of like hard. But again, it's the same topic. It's deflection for this. I want to mention one thing before I get going. I appreciate Nima's camera and stand, so he helped me with that. Thanks a lot. So I will do statics video, but for now, let's say we know that this is omega naught L over 2. This is your omega naught L over 2. I don't have any discontinuity point. Thus, I could cut a section here. But if you have a point load here, for example, you cannot jump in here. You probably need to discretize your beam. Okay? So, let's see. Well, using a cross-Hardy method, this is your V, so I don't really need the V, so I'm making it small. This is your M. So some of the moment at the section, counterclockwise positive, that gives me M of X 2, or omega naught L over 2 times X, that's minus omega naught L over 2 times X. This is F of X, this is X. That's a product, that is a function. And again, I'm going from here to there, so that is a counterclockwise moment. So then plus, you have this dummy load, omega naught L, but it's not L anymore, it's X, because everything in terms of X. So omega naught X times centroid is half of the total beam, so X over 2. So let's just solve M of X equal omega naught negative omega naught X squared over 2 plus omega naught L over 2X. So I'm going to erase the top, because we don't really need that part. So much fun, right? I am having fun. I hope you guys are having fun too. Okay. So second derivative of deflection is m over EI. Let's just quickly double check. If you guys remember, here's a beam, looks like this. The maximum moment is what? Very common, omega naught L squared over 8. You see it all over the place. Let's plug L over 2 to see if that's right. So forget about omega, forget about L. So let's see, 1 over 2 squared. It's minus, plus 1 over 2 times 1 over 2, right? So I'm taking omega naught L out. So I'll have 1/2 of L. So I'm taking that out. 1/2 squared plus 1 over 2. X is 1/2 in the middle. That is 1/4. This guy 1/4. Minus this guy is 1/8. And that's 1/8, right? Multiply by 2, multiply by 2. That gives you 1/8. So, should be good. So I'm going to take EI out, because it's constant. Let me just take a sip of coffee. So I'm going to say EI second derivative equal omega naught x squared over 2 plus omega naught L over 2x. And now this is a differential equation, right? So ordinary differential equation, separable equation as we talked last time, integrate both sides. So EI, integral of this, that gives you just the first derivative, right? One integral with one derivative. So this is negative omega naught over 2x to the third over 3 plus omega naught L over 2x squared over 2 plus the constant C1, let's call it. Integrate again, EI first, or the deflection. That, by the way, this equation, or this constant, or this parameter called rotation or slope. So then integrate one more time, negative omega naught over 6 x to the 4 over 4 plus omega naught L over 2 and 2, and then x to the third over 3 plus C1x plus C2. Well, those called, or I would probably rephrase my statement saying, to get C1 and C2, you need something called BC, boundary condition. The boundary condition could vary from a beam to a different beam. So for this, we know that the deflection at A, B, 0. So we could say y of 0 is 0, y of L equals 0 to get C1 and C2. By the way, if you have any question, I am going to solve this problem only, and I'm going to give you for my class at least, give you the chance to practice by yourself and then come up with questions. Send it my way. I could solve it on the board here. So let's just erase this part because we need that thing. And it's snowing in Denver. It is beautiful outside right now. Look at that view. Coffee snow, and some deflections problem. So y of x, ei equal negative omega naught 6 times 2, that is 24, x to the fourth plus 2, 2, 3, that's 12 omega naught L over 12, x to the third plus c1 x plus c2. I've got a request already for calculus, review calculus, so I'll see if I could start with calculus next week. Well, if I do y of 0 equals 0, easy enough. 0, 0, 0, 0, that must be 0. So by inspection, C2 equals 0. Y of L equals 0, that gives us what? 0 equal, I'm going to take omega naught out. And it must be, you know, basically something common, which would be L. But I'm not going to do that right now. L to the fourth, I have minus over 24 plus L to the third, L to the fourth over 12 plus C1L equals 0. Right? Obviously this is this, and then that's, oops, sorry, that's by itself, because omega naught is common for those two terms. And this is 4, if you can't see, I'm going to make it bigger. So if you solve that, so C1 equal, C1L equal, omega naught, then we're going to multiply by, because I'm moving this from here to there, so I'm going to multiply this by negative. So that would be L to the fourth over 24, not 12. Minus L to the 4 over 12. So you could see clearly that C1 equal negative omega naught L to the third over 24, right? Multiply here by 2, 2, 1 minus 2, negative 1, omega naught L, cancel out with L to the third over 24. So this is your elastic curve or deflection equation. Let's write that down. Up, up. So I have negative omega naught L to the third over 24, and this is 0. Any questions so far? Sip of coffee. Give you a break to catch up with me. So your y of x equal negative omega naught x over 24 x to the fourth plus omega naught L over 12 x to the third minus omega naught L to the third over 24x. Right? So let's plug L equal, or I'm sorry, x equal L over 2 to see if that would be equal 5 over 384 omega naught L to the fourth. It looks like it's going to be L to the fourth. It looks like it's going to be omega naught. It looks like the bottom going to be, or will have EI, the flexure stiffness. So actually we need to care about only the coefficient. So EI y of L over 2 equal, I'm going to take y, I'm going to take omega naught out, and L to the fourth Because L to the third, that's L to the fourth, L to the third times L over 2, but let's just say L, that's L to the fourth. So that will be negative 1 over 24 plus 1 over 12 minus 1 over 24. Right? So that would give you what is omega naught. Obviously, we forgot to multiply by 1 over 8. 1 over 8. But let's just, I probably confused you with this step. So let me just plug, could just discard that step and just say negative omega naught over 24 times L over 2 to the fourth. Maybe that makes more sense for you, because I'm pretty good with simplification, so sometimes I feel like I confuse you or confuse people with my simplification thing. Now I could do that, right? 1 over 24. 1 over 2 to the fourth, that's 1 over 16, plus 1 over 12, 1 over 8, minus 1 over 48. If you do this, you should come up with 5 omega naught L to the fourth over 3A4, and then you divide it by EI, and you have minus, right? But, or you could probably say just minus here, but it doesn't really mean anything, the minus. It means that you're going down, basically. Positive and negative in engineering doesn't mean anything. It's just your reference. So I'm in the moment making counterclockwise positive. Well, if I do clockwise positive, nothing's going to happen. Everything is going to clear out when you solve the entire problem. Does that make sense? That is about all what I have for today. Again, I'm going to recap that. So, finding the deflection, you need to find the moment expression first, and then integrate it twice. And once you integrate it twice, you're going to come up with, a differential, a particular solution, right? Or first general solution and then particular solution. Then once you do that, you could come up with BC, boundary conditions, or math perspective, IVP, initial value problem, initial conditions, whatever you want to call it. Then what is next? Next, you're going to plug your initial conditions, or BC, and then find the particular solution, and then plug any value along your beam. That should give you a deflection at any specific point, right? If you have any questions, please leave some comment. And I've basically told you guys and provided you with my number and my email address. So don't hesitate to give me a call or text me, say, well, could you explain this problem for us? I will. So this is for chapter 11/12. I know there is a lot of plenty questions, but this is the main idea. So I'm gonna leave you with that, and practice, study hard, and keep hitting the wall. You will eventually, I believe in you, that you're gonna break it. I will sign out for now, and I'll be waiting for your comments. Bye-bye.